Okay. So we have manifolds loss and one possible additional structure. Is a connection. On some relevant vector bundle. Okay. Another additional structure of interest which might be of interest is a non-degenerate Riemannian structure. And today here, G then is a Riemannian metric. Simply means that G is, I'll just write out, is a section of the bilinear forms on the tangent bundle, which is symmetric and positive definite. Okay? Yeah. Oh, positive definite. That's what you were smiling. I'm sure I did that many terrible things. Okay. So, Riemann certainly considered these things, and the fundamental remark is which I will sketch, I hope, is to sketch a proof of this remark, is that given such a G, now I'm responding to Anna Maria, or is that right or not?
Maria.
Just Maria. I never know. I'm sorry. To her, to her remark, what's given, what's going on here, right? So I will try to be consistent. Given is something, and then given that, we do something. So given a Riemannian metric, there is a canonically associated connection. which one is compatible with the metric. Let's say, given a Riemannian metric G, compatible with the metric. And 2 is torsion free. I have to tell you what those things mean. So there are two conditions, and if you think about it for long enough, they're very natural conditions. I had to think about the second condition a very long time, but I'm beginning to see that it's very natural, torsion-free, whatever it means. It seems to me it's a very natural condition. And the first condition is obviously natural. And given such a thing, there's a canonically associated thing. So canonically means it is unique with these properties. Whatever these properties are. So I'm going to talk about these properties now. Okay. You give me a metric. It's more like Riemann gives Levi-Civita a metric, and Levi-Civita produces this canonical. This is a theorem of Levi-Civita. So what is 1? The same as this for every vector field. So a connection is defined on, it tells you how vector fields act as derivations. Vector field on the manifold. And well, let me just I interpret, sorry. So for all so I haven't written this carefully, so I'm sorry. Oh, okay. I have written it carefully. I'm talking about the tangent bundle here. I'm talking about connection on the tangent bundle. Okay. Talking about taking derivatives. Okay, so it's okay. So connection 1 is for all x, y, and z sections of the tangent bundle, so vector fields. It follows that x applied to G of y of z. I want to make sure you understand what that means. So you take a vector field, take another vector field, apply the metric to it. You understand that's a function. Is that clear? Because the vector fields are varying from point to point, and the metric varies from point to point. Everything's varying from point to point. So that's a function. And vector fields differentiate functions, so this makes sense. Right? And you should think calculus, the product rule. So the product rule is you differentiate this first thing and you add it to the derivative of the second thing. Doesn't that look like the product rule? Now, this is differentiating, this is a function, so you're differentiating the function as usual. And it says you differentiate this function as usual by first differentiating inside the bilinear form, the first thing, and then the second. This is some sort of product rule called compatibility with the metric. I'm going to talk about what that really means. Okay? And the other condition is torsion-free. It's the condition is for all x and y, which are vector fields. So we're talking about connections on the tangent level, vector fields on the manifold. The derivative of y with respect to connection x minus the derivative of, with respect to y of x, is nothing more than the Lie bracket xy. And if you think about that, it's called torsion-free, and it has to do with how things are somehow measuring how things are twisting around along curves. I think it's a non-trivial condition. Let's just regard it as an algebraic condition for now. So torsion-free and compatibility with the metric. Okay, those are two conditions. This is compatibility with the metric. This is torsion-free. And the statement is there's a unique connection which satisfies these conditions. This connection is called the Levi-Civita connection. And for those of you who are interested in for example, relativistic situation or something where you have non-degeneracy but not positive definite, you will see the proof has nothing to do with positive definiteness. It has to do with non-degeneracy. Okay? So this is also okay for pseudo-Riemannian things. So also okay for pseudo-Riemannian measures. Okay. Now I want to a feeling for this, what this sort of means. For number one. In a frame, you write the y, x, y, and z, and so on. You write y and z in a frame in terms of the frame. So you write g of y and z is something like in a frame. That means with the symmetric matrix and all that stuff, it's probably something like yi, gij, zj. Isn't that true? Right, you just write the code, right? Okay. And now everything is varying. The vector field y is varying over the manifold. The metric is varying over the manifold. The vector field z is varying over the manifold. So you take the derivative of this thing with respect to x, and that's taking the derivative of this thing, this whole terrible thing, right? That's a terrible thing, but it's a differential operator, right? And so you know what it does. It means you take the derivative of the first thing times the rest of it, plus the derivative, the first thing times the thing in the middle, times the rest of it. Oh, there's a j here. Plus, finally, yi, the middle thing, and the derivative of the last stuff. I'm being very rough here, but you see what I mean. Right? Of course, there's some matrix here that tells you that I don't care. But look, this is the derivative of the first thing. That's that. Right? G times the derivative of the first thing. This thing here, this is all figurative, but it's explaining what's going on. This thing is the derivative, is the last thing here, but this thing doesn't appear. Right? The statement, compatibility with the metric, means that middle term does not appear. Okay? It means the middle term is 0. So the meaning is the derivative of the metric with respect to any vector field is 0. That's the meaning of it. Okay? It means when you differentiate it, you get 0. It means it's constant with respect to the connection. It's a constant with respect to the connection. It's a constant with respect to the connection.
But we haven't talked about the derivatives of bilinear form.
That's right, I have not talked about derivatives of bilinear form, but you can believe me that if you have a connection on the tangent bundle, I can get connections on tensor bundles and so on. So, I mean, I told you the bilinear form is just the twofold tensor product of the dual bundle. So I have the dual connection on the dual bundle and then the twofold tensor product. I mean, everything is canonical once you start on the tangent bundle. On all possible tensors. She's going to make a terrible remark to me. What are you going to say?
Well, what are the vector spaces on the tangent space of time, right? Because you said that x is in the vector space of Tn, right? So what do you mean by that?
We start with 3 vector fields.
Yes. So is it a typo over there, like on the
Okay.
left
Right.
down? The
So-
vector space of
So you agree? This is only figurative. I mean, you're different. I'm just saying you have 3 things you have here in this thing: the metric and the 2 vector fields.
yes, and there are vector fields on the manifold, right?
That's right.
So not on the tangent space of the manifold.
No, the vector fields on the manifold. Did I say something?
Yeah.
No. Oh, no. Okay. You get what I'm trying to say anyway. There are 3 things going on here. It's a pairing. It's a pairing, right? Don't look there if you don't want. But g of y and z has 3 things varying. G, y, and z. And they're varying in this way, right? In a bilinear way. It's y, g, as a matrix, z. There's some coefficients in there and so on, but don't worry about it. It's saying that if covariant differentiation of the metric makes sense, it means that this connection is 0 on the metric. This means this metric is constant with respect to this connection. Whatever that means. You know? I mean, come on, this can't be too bad because, again, if you have a connection on the tangent bundle, you have a connection on the dual bundle just by duality, you just write it down. And then you have a connection on any tensor product. So you have a connection on the space of bilinear forms. Okay? So you have what that thing means. I haven't talked about it yet, I will talk. Okay? We will see that this means parallel transport well, it says the metric doesn't change with respect to the connection. Yes? So parallel transport along a curve is an isometry. Believe me, that's really interesting. Well, right? Again, the vector fields get differentiated. But the metrics, in this, when you're taking a derivative here, the metric's also going to get differentiated. But the derivative of the metric does not appear on the right-hand side. So that means the metric, when you differentiate that part of it, is 0. Okay? That means when you, because the connection tells you how to go from one place to another, it means that along a curve, parallel transport is an isometry. Yeah. Isn't that interesting? So it's a formal algebraic condition, but it's a very important condition. This other condition is a little bit deep. So, maybe I will not. This is the wrong time to prove this theorem because it's technical. It's not hard, but a lot of fooling around. So let me avoid the proof right now. I'll give it next time. If you don't, I mean, you're tired. So am I. Okay. Or if you like, I'll give you the idea of the proof. Would you like? Okay. Let's try. Okay? This is really a test of humankind. Okay? So, okay. The idea is an idea of this man. This is Cozens' proof. And it's related to, he's another mathematician in Strasbourg. Let me try. So I'm going to write something down here. X, G of Y, Z, plus Y, G of Z, maybe ZX, minus Z of G. I try to be consistent with the permutation. X, Y, Z, and now X has gone back here, and Y has gone front. Z has gone up front. How do we get Z up front? Is X, Y, Z? Or maybe just X, Y. Okay. You're going to hate me for this. Well, probably I'm going to hate myself. Okay. Now, I'm going to use star. And star is this. That's the only thing I have to use. I'm going to use it. Right? Okay. So, here we go. This is G of delta with respect of nabla x, y. Okay. And now physics people will like me because I learned how to cheat from physicists. Yeah. No, you cheat and then you recover from cheating. Right? That's the only way. So I want to use the condition torsion free. So here's the condition torsion free. dx of y. I have dx of y. And from back in here, am I going to get dy of x? No. Right? dx of y. I would like to get dy of x. Okay, z plus g maybe I'm going to get something here. Aha! No, I don't get this here. This is terrible, I don't like this. Okay, now, I will continue on. Aha, this is G of nabla Y of Z. Aha, 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 aha. Here I have nabla Z of Y. Minus nabla Z of Y. Right? Minus nabla Z of Y, nabla Z of Y. Right? I hope that's right. Nabla Z of Y of X. Now, did I cheat? No, I don't think so. Do you agree with that? I told you you wouldn't like this. So I get a minus, I have nabla Z of Y here with minus sign, right? And X. So I get this term nabla Z of Y with a minus sign and X. And here I have nabla Y of Z with a plus sign X. Right? So that's that. So I've taken care of one minus sign. That's great. Okay, and this thing I'm going to use, this thing here is what? What is this thing? It's nabla, this is YZ, right? Right? Now what else, where else can I use a minus sign? What did I use here? I used nabla Z, did I use nabla Z of X? No, I haven't used nabla Z of X with Y. How, oh, this is really terrible.
Use it with the first.
Hmm?
So nabla Z of X with Y, and then you have nabla G, Y, nabla X of Z. Second term.
The second term,
Below. Yes.
here,
Yes, with what comes with the last.
oh, great. You're saying that I can, you're saying I can put this together with that, is what you're saying?
Yes.
And what I've already used is nabla Z of Y, so I have used nabla Z of X. And if I put, and Y, and I put it in here. So this is nabla's, this is G of nabla X of Z minus nabla
Z.
Z of X. Why? Have I dealt with all terms? So this term has been dealt with. Oh, this term has been dealt with, because you just told me how to do it. Anything else? Have I forgotten anything? This term is now ZX. Have I done everything?
I think so.
Huh?
Yeah, I think so.
There should be one more term.
Why, coming from the second one, we are missing something that has a lambda y.
Oh,
Yes, lambda y. Yeah.
Yeah. G nabla Y X Z.
So is this okay, except I've left something out, right?
Yes.
What did I leave out?
G nabla Y X and Z.
So I should write G of nabla Y X? That's what you're saying?
Nabla Y. So Y is
Y, so nabla sub y.
Nabla, I'm sorry, nabla Y of what?
X and Z.
X and what?
Z.
Z.
No, that's just that.
Oh, I canceled.
No, it's the other.
No,
That's
it's
because it.
Huh?
asymmetric.
Yes, yes.
No, but it's different.
It's symmetric.
But that still is a difference, you know?
Yes, it's
Makes sense. Yeah.
That's okay.
That's fine, yeah.
Okay. Really? Oh, okay, it's not bad, is it? So I have that term twice.
Yeah,
No,
no.
no, I don't have that term twice.
Different term.
Okay, you're right. So what I need to do is cheat and subtract off nabla, I'm going to subtract off nabla x of y and z, and I need to put a 2 here. All right? Right? So I want to force that torsion condition into this calculation, right? So look at this. Look at this. This is Cozens' calculation, I think, I hope. Is that this left-hand side equals, I'll write it again. Well, here it is. Oh no, I'll write it again. Equals 2 times nabla x, y, z. Now I'll write the 3 things in there. It's wonderful. Y, z, x plus nab g of z, x, y. And then the final term is g of, well, that's not f, z, yeah, and g of y, x. Let's see. Okay. Sorry. So I will now excite you with Cozens' formula. Cozens was a great mathematician in Strasbourg. Cozens' formula is G. I'll write it down just to make it crazy. The first thing is, okay, equal. Let's write Cozens' formula down. The left-hand side. And let's call this thing in here. Let's call this thing dagger. Plus dagger. Okay? Okay. So with a little help from my friends here, you have G of nabla x, y, z is equal to the left-hand side. You see it up there, right? I don't know why I canceled that out there. This is in the left-hand side. Okay? Now stare at that for a minute. What's the left-hand side? X, Y, Z. X, Y, Z. Z, X, Y. What's in the box? D bracket Y, Z, X. D bracket Z, X, Y. D bracket Y, X, Z. And every place symmetric. Do you understand that the left-hand side is defined by the right-hand side? I do not need to know the connection to the right-hand side, do I? The right-hand side is not involved with a connection, right? You see it anywhere here? It's nowhere there, right? The connection is nowhere on the right-hand side. The metric is on the right-hand side, the Lie bracket is on the right-hand side, but never the connection. That this equation defines nabla x of y uniquely. Right? For all, well, because it's true for all z. Right? Do you get it? Maybe it's a good point to talk about. Do you get what I'm saying?
Where did the left-hand side come from? G of
Right here.
left.
Oh, I'm sorry, two.
Okay.
I just took this calculation that you helped me do, and we killed everything that involved nabla except for one term. Right? Using the condition torsion free. Right? And if you have a bilinear form where you know what this is on all possible vectors, then you know what the nabla is. Right? Right?
So this equality is by the metric compatibility.
This is the
The last.
what did we prove? We proved using the metric compatibility and torsion free, you get a formula.
Yes.
So that is the statement that metric compatibility plus torsion free determines the connection. Right? There's the formula for it. Okay? So this is Cozens, it's called Cozens' formula for the connection. If you like. Okay? And now, you're thinking, so tell me what you're thinking about.
Should be a minus, and it's a minus.
Yes.
Probably there is a minus sign. So it's minus dagger. Is that what you mean? Yeah. Okay. So this terrible thing is a formula for the connection. Okay. If the connection satisfies those two things, this is a formula for it. So this is a uniqueness statement. So is it clear what we have to prove now? We have to prove that the thing that's defined in this way is really a connection. We have to prove three things. The thing that's defined in this way is a connection, it's compatible with the metric, and it's torsion free. So this is a horrible job. I think you can actually have a computer do it. Right? I think so. Because all of these, you have to prove it's a connection, prove that it's metric compatible, and prove that it's torsion free. You just go through this definition and check it. It's horrible. Okay. But Cozens did that, and so, well, Levi Civita did that, but this is Cozens' idea to write down this formula in this way. This is Cozens' trick of writing the top thing down, then the rest of it any normal human being can do. Okay. So, and then prove that nabla defined in this way is a connection on the tangent level, of course, satisfying those two conditions. Nowadays standard way to do that. Okay. There's a unique metric connection, which is torsion free. This is called the Levi-Civita connection of the Riemannian metric. If you think carefully, using this connection, the derivative of the metric is 0. The derivative of the metric being 0 means that if you do parallel transport by this connection from one place to another, it is an isometry. And that's exactly the way our classical giants were thinking. Parallel transport should be an isometry. But they were thinking using this Levi-Civita connection. Well, there's one last thing that I mentioned. There are two things that need to be mentioned now. I will tell you what they are, but I will not go into detail because we're all tired. Okay? two basic points. Must be discussed. First basic point that needs to be discussed is the notion of geodesic. And the second basic point that needs to be discussed is holonomy. Both are really, really interesting, really fundamental. There are two ways to discuss geodesics: via the connection and via distance. Let me comment in the remaining time on these 2 points. I think we all have some feeling of what geodesic should be. It should be the shortest thing. But actually, the easiest first way to talk about is with respect to the connection. Geodesic should be straight. Should be a straight curve, whatever that means. Now think about what it means in the plane. A geodesic should be a straight line, and you have the velocity vectors around this, on this line. This is the velocity vector, this is gamma point. And in the geometry of the plane, if you take the start at the first point and take the velocity vector here and transport it, it stays parallel, it stays along the line, it stays, because this line is straight, when you transport it along here, it stays tangent to the line, it doesn't move. It says that the parallel transport of the velocity vector, well, it says the derivative of the velocity vector with respect to the velocity vector is 0. It stays parallel, it stays straight. You get it? You move along the curve with this velocity, and you go by parallel transport, and you stay parallel to the curve. That means you stay tangent to the curve. This is what that means. That's parallel transport of the velocity vector. So, geodesic, in the sense of 1A, is a curve gamma such that star holds. Parallel transport along the curve of the velocity vectors is the velocity vector. That's a statement of straightness. This equation star is a second order ODE. Do you see that? That's almost clear, because where did I do this ODE business? Oh, I didn't do it. Remember, in coordinates, I got parallel transport is a first order ODE, but now I'm taking derivatives of the derivative in this discussion. So this is a second order ODE. And for a second order ODE, the initial value is the point of the initial value and the velocity of the initial value, all right? And that just says, if you fix the initial value and the velocity of the initial value, the velocity vector, of course, you have a unique geodesic, and that's what you believe. Okay? That's what I'll talk about next time. 1B is minimizing distance. Okay. So you're looking for a curve, gamma, from curve gamma 0, maybe no particular endpoint gamma, yeah, maybe move gamma 0 to gamma 1, let's make it a concrete curve, smooth curve. At least locally, no self-intersections, and so on, gamma p, which minimizes the integral, say from 0 to 1 is a curve of the length. So the length of the length, which is the norm of the tangent. This is the length of the curve with respect to the metric. Please notice in the first definition I only use a connection. Yeah? In the second definition I'm using the metric. Okay. So 1b is this is a connection notion, and the distance notion I use the metric. Okay. Well, it's almost time to go. This is a fundamental problem in mathematics and physics, not just length. You have all possible curves. Let's even change the notation to convince you that it's more general. Given a curve, there is some way to measure energy, whatever it means. You have what we call an energy functional on the curve. I'll call it energy. I just don't want to call it length because I don't want to be so special. Okay? So this energy is given, well, let's call this length, but now let's call it energy of a curve is the integral of some very complicated function of the curve and its derivative and so on, dt. Now you believe me, this appears. Yes? So this would be here's an example of an energy functional on the curve. It's called length. Here's a general thing. The energy of something is some complicated function. Maybe it's curvature function, maybe it's something else, I don't know, of the curve. And the job is to find a curve which minimizes that. So the job is to minimize the energy function. Okay. And in calculus, you learn how to do that. In high school, you learn how to do it. You take the derivative, right, and you set it equal to 0, right? And it should be, you're hoping for a minimum, And so what you do is you look at the second derivative, right? Okay? And if the second derivative is negative, then you're really happy because, no, positive, right? The second derivative is positive, you get a minimum. Okay. So you have to know what it means to take the derivative of an energy function like this. And this is the first step in a subject called the calculus of variations. Okay? Because you are varying the curve, nearby curves, and you want to have your curve be this minimal energy. So it looks like this. The minimal energy. The nearby curves have more energy. You're trying to minimize energy. For those of you who have some feeling for Morse theory, this means you're going to have some flow to minimal energy. Gradient flow. You can think of gradient flow to minimal energy. You would like to do that. So this is called the calculus of variations. This is an old subject. This is far older than the notion of connection. And associated to this problem is something called the Euler-Lagrange equation. I hope you know the ages of these guys, Euler and Lagrange. This is long before the stuff I've been talking about, right? The 18th century, basically. Okay? Very interesting. This is a differential equation that the curve has to satisfy to minimize the energy function. Guess what? It's a second order differential equation. Guess what? The second order differential equation, if you take the Levi-Civita connection, yes, for 1A, so 1A Levi-Civita, these differential equations are the same. Okay. So what you believe about straightness, namely parallel transport, doesn't change the metric, the tangent as you're going along. Yeah. Straightness and minimizing the energy function are the same thing. It's the same differential equation. Okay? That's a very interesting thing. Now let me make a last remark, and just so you know where we're going on this subject. The second order equation, you should never think about it as a second order equation. Second order differential equation. I hope you've learned a little bit of mathematics. For example, do you see this equation? X, you see this equation? You see this? This equation, you've seen equations of this type, right? Oh, yeah? I hope you know how our classical giants solve this equation. They say, well, we define u to be equal to x and v to be equal to x point. This also comes from, yes? And so this becomes a system of equations, u equals x and v point equals lambda times x, which is u. So you never, ever want to solve directly a second order equation. You make the substitution so you get a first order system of equations, right? Yeah. And a first order systems of equations, you have two variables, the location of the particle and its velocity. Guess what? The location of the particle and a velocity is a point in the tangent bundle, or the location of the particle and its velocity is a point in the tangent bundle. This differential equation is a vector field on the tangent bundle. Okay? With the metric, the tangent bundle is canonically isomorphic to the cotangent bundle because the metric is just a pairing. On the cotangent bundle, there is a canonical symplectic structure. If you have a symplectic structure and a Hamiltonian, I'm speaking to physicists now, there's a way of understanding Hamiltonian systems. Geodesic flow is exactly the associated Hamiltonian system on the cotangent bundle. This means symplectic geometry is embedded in this subject. Let me say it again. This second order equation you never want to solve. You go to the first order system. The first order system is a differential equation on the tangent bundle. But the tangent bundle using the metric is isomorphic to the cotangent bundle because you can use the metric to find the isomorphic. On the cotangent bundle is a canonical symplectic structure. If you have a symplectic structure and a Hamiltonian, you know what it means a Hamiltonian vector field. And you know all about Hamiltonian dynamics. Guess what the Hamiltonian function is? Guess. It's the only function associated to this. It's the norm function on the tangent that's given to you by the metric. So this is, and the dynamics of this Hamiltonian flow can be understood by a lot of interesting modern mathematics. Okay? It's called geodesic flow, and you really want to understand the dynamics of this flow, and so on and so forth. So we're getting close to some really interesting stuff, particularly because you have these two things, second order equation, tangent bundle, cotangent bundle, and so on. Okay. That's one of the goals of where I want to go. So thank you for today. It's been a long day. I apologize.